we will prove in this lecture that the first theorem of isomorphism. What is first theorem of isomorphism? Okay, so we have a linear transformation T from Vf to Wf where F is a field. Be a linear transformation. Then first theorem of isomorphism says that V by kernel of T is isomorphic to image of T. Okay, so this is a quotient space. Okay, quotient space. We have seen in my previous lecture that this is a quotient space and how the operations are performed in this space. If you don't know, then please visit my lecture number 12. You will learn that how we add two elements in this space, how we multiply a constant to a vector. Okay, now in this lecture we will prove this theorem that V by kernel of T is isomorphic to image of T. Okay, so firstly here we will see that V may be finite dimensional or infinite dimensional. Okay, it is easy to prove in finite dimensional, but we will learn in both infinite and infinite dimensional. That so what we need to show is there exists a function from V by kernel of T to image of T. Okay, we need to construct a functions from V by kernel of T to image of T, which is for isomorphism, which should be firstly that function should be linear. Second, that function should be 1, 1, and third, that is onto. Means if these three conditions holds, for any function, then we say that function is an isomorphism. Okay, so we know that element of V by kernel of T is look like V plus kernel of T, where V belonging to vector space V. Okay, and image of T has an element of the form of T of V. Okay, image of T is this collection of T of V such that V belongs to V. Okay, so it has element of the form T of V where V belongs to capital V. Okay, so we have a domain V by kernel of T and codomain image of T, and we need to construct a functions from this set to this set. Now question is that how we define a functions from one set to another set. So we take an element from domain set and find the image, what will be the image of this element in the codomain set, and we have every element has an image. Okay, so take an element from V by kernel of T. So we can take V plus kernel of T as an element of V by kernel of T, and their image take T of V. Okay, and now we will see that this is actually a functions. So how we check this is a functions? Firstly, we have to check for every element V of V by kernel of T, we have an image. So as we have taken an arbitrary element in this set, okay, V plus kernel of T, and that element has an image. So every element of V by kernel of T has an image. Okay, and we need to check is there an element which have two images or more than one image. Means every element of the domain has an image, and secondly we need to check for one element we should not have two images or more than one image. Okay, so take v plus kernel of t equal to v dash plus kernel of t. This is an element of the domain. Okay, and we have taken that both the element is equal. Since this is equal, we need to show f of v plus kernel of t equal to f of v dash plus kernel of t. For the well-definedness, we are checking here well-definedness of the given function f. Okay, we need to prove that this is a function. Okay, so what we do here, f of v plus kernel of t equal to t of b by the definition of f. Okay, how we define f here, f of v plus kernel of t is equal to t of b, so it is equal to t of b, and now we can write t of v as t of v minus b dash plus b dash, because we can cancel out b dash and b plus b dash and minus b dash. Now as t is linear, initially we have supposed that t is a linear functions. Okay, functions from v to w, so t is linear. So by linearity, what we can write, t of v plus v dash equal to t of v plus t of v dash. So it will be t of v minus v dash. This is first vector, this is second vector. If you assume, then it will be t of v minus v dash plus t of v dash, because of t is linear map. Okay, now we know that v minus v dash belongs to kernel of t, because this is equal, and it is if and only if condition that if v plus kernel of t equal to v dash plus kernel of t is equal, then v minus v dash belongs to kernel of t. And what is the definition of kernel of t? That element will be in kernel of t such that their image is zero vector. Okay, so this image is 0, and we have left only t of v dash, so it will be equal to t of v dash, and by definition of f we can write it f of v dash plus kernel of t by definition of f. It means we have f is well defined, means it is a function. Okay, how we define this function is we have taken an element from v by kernel of t, which is of the form v plus kernel of t, and that is equal to t of v. Okay, this is an element of image set. This is an element of image set. Okay, now we will show this function is an isomorphism. So to show f is an isomorphism, what we need to show? Firstly, we need to show f is linear. Secondly, it is 1 1. Third, it is 1 2. Okay, so we will prove it in a step by step. Please watch till the end, then we will understand how this works. Okay, and also subscribe my channel, because if you subscribe, that will be very helpful for me. Okay, so we will prove the linearity of f. Okay, so take two element v plus kernel of t and v dash plus kernel of t, and these both element is of in v by kernel of t. Okay, so f of v plus kernel of t and v dash plus kernel of t need to show what? F of v plus kernel of t plus f of v dash plus kernel of t. Then f will be linear. We can have f of v plus v dash plus kernel of t, because in the quotient space we have added two element. Okay, you can see my previous lecture, video lecture 12. Okay, you will see there how we add two element in the quotient space. Okay, so we can write it, this is equal to v plus v dash plus kernel of t. how we add two element in the quotient space. Okay, so we have b plus b dash plus kernel of t, and by definition of f, it is equal to t of v plus v dash. Now as t is linear, we have t of v plus t of v dash, and by definition of f again, we can write where t of v equal to f of v plus kernel of t, and t of v dash equal to f of v dash plus kernel of t. Now see, f is linear. Okay, also we have to show for linearity that alpha belong into field, then f of alpha v plus kernel of t equal to f of alpha v plus kernel of t, and by definition of f, this is alpha v, and as t is linear, we have alpha out, and it will be by definition of f again, it will be alpha of f of v plus kernel of t. So now it is linear. Okay, we have proved that f is linear. To show f is 1 1, okay, so assume let v plus kernel of t and v dash plus kernel of t, this both belong into v by kernel of t. So assume this is equal, image is equal, and we will show pre-image equal, then f will be 1 1. Okay, so we need to show this is equal. We will show v minus v dash belongs to kernel of t, because this is if and only if condition. If this will be equal, v minus v dash belong to kernel of t. Okay, as f of v plus kernel of t equal to f of v dash plus kernel of t, this will be t of v plus t of v dash by definition of f. Now we can write it here, t of v minus t of v dash equal to 0, because if we take it in left side, it will be minus t of v dash equal to 0 vector. Okay, now by linearity of t, we can write t of v minus v dash equal to 0. Okay, and since this image of this vector is 0, it means this vector will be in kernel of t. Okay, see the definition of kernel of t. So, and that is what we need to show. This means f is 1 1. F is 1 1. Now we will show that f is onto. Means what? This is v by kernel of t. This is image set of t. So for any element we should have an image. Then the f will be onto. So take any element, an arbitrary element from image set of V, and we have to choose pre-image. Okay, so take V plus kernel of t belongs to V by kernel of t, and check that this element has image as t of V by definition of how we defined f, by definition of f. So for any element t of v, we have an image v plus kernel of t, and this belongs to v by kernel of t. Okay, please, if you have any queries, please ask in the comment box. I will surely answer your questions. Okay, so now we have proved that f is function, linear, 1 1 and onto. So f will be an isomorphism. Hence v by kernel of t is isomorphic to image set of t. Okay, thank you.